Thanks very much. So this is a big collaborative project, so thanks very much to my co-authors there. And it's a bit of a mixture of meteorologists and oceanographers who have got together to work on this. I'll just put my watch there. So this is work that's come out of the Iceland-Greenland Seas Project, which is a YOP-endorsed project, you'll be pleased to hear. It's sort of encapsulated by the statement there, Coordinated Atmosphere Ocean Research Project, centered on a rare wintertime field campaign, which is seeking to determine the location and causes of dense water formation during cold air outbreaks. And you can see that we had a research vessel there, and with photographs from an aircraft, and it was in wintertime, so we had some wild weather, as the photograph illustrates. Here's a bit of a cartoon of the resources we had. Twin Otter research aircraft, a research vessel with a 40-day cruise, and a bunch of atmospheric and oceanographic measurements from that research vessel. And then we also had sea gliders, and then longer-term measurements from an ocean mooring and a buoy, a meteorological buoy. So it was very much trying to sample the atmosphere and the ocean in a sort of coupled way, and then try and put those observations together to study sort of coupled processes. And incidentally, we've got a poster which uses a lot of these observations to evaluate ERA5 and the Met Office model. So if you're interested in sort of the marginal ice zone and this region, then you can have a look at that poster. So coming back to the cold air outbreak case study, well, here's a sketch of typical cold air outbreak, cold air coming across the sea ice and marginal ice zone, cold air warming rapidly with the wiggly arrows there indicating heat fluxes out of the ocean into the atmosphere, and that's changing the atmospheric boundary layer structure. What was novel about this work really was being able to simultaneously measure the atmospheric cold air outbreak and the ocean response. Top row here is, these are some synoptic maps, and so the synoptic maps are from ERA5, and the panel on the right is obviously a satellite image. The top row is from early in the cold air outbreak, and the bottom row is a few days later, 4th of March, where it's sort of at its peak, as it were. And the left panel is showing a cold air outbreak, a couple of cold air outbreak indices. So the shading is cold air outbreak depth, and the sort of amber contours are a cold air outbreak index. So they're both giving you an indication of the strength of the cold air outbreak. So early on, it tends to be confined up here in the northern Greenland Sea region, but a few days later, the sort of cold air is swept down across the Nordic seas, and it's covering the whole region of interest. The middle panel's mean sea level pressure and heat fluxes at the surface, and you can see that heat fluxes have really picked up during the peak period, and especially along the sea ice edge here. And the satellite image is giving a bit of indication of the sort of transition from shallow convection to much more active, exciting-looking weather conditions, as it were, on the 4th. A couple of time series indicating the evolution. So the left panel is from a buoy, and the right panel is from around 30 radiosonde releases from the research vessel. So this is you can think of this as a time series. I mean, the ship is moving, but it's not moving very much in terms of the scale of the cold air outbreak. In terms of evolution then, we've got relatively mild conditions and then this rapid drop in temperature of a few degrees. And you can see that both in the buoy here and also in this very tight temperature gradient at the beginning of the time series. It's around 10 days here and around 13 days here. And then I've shaded the peak period, so the 4th of March period, so where there's a second sort of cooling, and this is where the wind has initially gone from sort of southerly to northerly, northeasterly, and then it becomes a little bit more northerly again, and the heat fluxes pick up to over 200 watts per square meter at the buoy. The buoy's a little bit off sea ice edge. So we've got some, you can use the radiosondes to sort of map out the characteristics of the atmospheric boundary layer, so you can see it's incredibly well mixed through most of the period. This is the sort of peak period here. Above the boundary layer top, atmosphere is very dry, and the wind speed, very strong, or relatively strong winds associated with the beginning of the colder outbreak, a bit of a sort of colder outbreak boundary layer front, and then stronger winds again later on. So, I mean, to summarize in a sentence, it's kind of a weak to moderate colder outbreak event, but it's remarkably long-lived, and with cold air existing in the region for almost a couple of weeks, really, by these sorts of data and by the metrics which I haven't shown you. We've been able to sort of combine together observations from the aircraft, which have got black outlines, and observations from the ship, which don't. And again, this is the early period in the left column and the peak period in the right column, temperature and wind speed. And you can see that by and large, the aircraft and ship observations match well, that the colder outbreak is relatively homogeneous. There's a bit of a gradient towards the ice edge, of course, but it's relatively homogeneous on the scale that I'm showing here, which is quite a zoomed-in picture. Oops. And we've also been able to sort of delve into the atmospheric structure a little bit. So red symbols here are from the 1st of March, when the cold outbreak's relatively weak, and the blue symbols are from the 4th of March. And again, this is aircraft data and some ship data combined. And you can see that we go from relatively warm temperatures of 264 through 266 down to around 262 as the colder outbreak sort of takes hold. And we've got observations of things like covariance wind stress, sensible heat flux, and latent heat flux. And you can see that at the peak, we've got much larger sensible heat fluxes, for example, especially at the surface, but also through the lowest couple hundred meters of the boundary layer. Okay, I want to turn now to the impact on the ocean, because I think this is what's probably the most interesting aspect of this study. And the ship did a huge amount of ocean sampling during this period. So during this sort of 9-day period here, we had I think over 100, more than that, sample CTDs, XCTDs, and XBTs. So these are all taking profiles of the ocean. We also had a mooring, which is indicated by the star, as I mentioned earlier, and a glider, which is roughly in the location of the diamond. And we've put all this data together to get a spatial picture. And one thing that's clear here is that there's really quite a strong difference between the boundary region, the boundary current region to the west, and the interior region to the east, so interior to the Iceland Sea. So the left panel is showing you mixed layer potential density, and the right panel is mixed layer depth. And there's a very strong divide in both of these ocean properties from these observations during this 9-day period. So the boundary current region has lighter water and a shallower mixed layer depth, the blue colors. The interior region has denser water, the yellow, and a deeper mixed layer depth, down to a couple of hundred, up 300 meters. And the mooring, which is obviously giving high resolution in time, but fixed location, is kind of in the boundary of these two regions. It's a little bit more like an interior location, as we'll see a little bit later. So what we've done is we've tried to look at the impact of this cold air outbreak on the ocean by using all of this data, but compositing it into two geographic regions, so the boundary current region and the interior region, and then looking at the early period and the later period. Okay, so we're doing this here. So the blue is the boundary current region, the blue symbols, and the red symbols are the interior region. And open symbols are from the beginning of the cold air outbreak, and the blue symbols are from later on, okay? The solid symbols are from later on. So what do we see? What we see is the mixed layer deepens in time between the open and the closed symbols, the early and the late symbols in all locations, but the mixed layer temperature only becomes cooler in the interior region, okay? So it cools down from here to here, but in the boundary current region, the mixed layer actually warms. So this is really counterintuitive because we've got this cold air outbreak sucking heat out the ocean. You'd expect the ocean to be cooling, right? And that's what we see here, but something else is going on in the boundary region. And there's quite a lot of profiles. I should just say that these symbols are showing the mean and a standard error. There's a lot of profiles going into each of these symbols, so this is not a sampling error or anything. In terms of salinity, there is a dense salinification over time in all locations. But it's much more of a salinification in the boundary region than in the interior region. Okay. I'm going to flick forward because this is an older version of the talk, but anyway. So we've done some numerical modeling to try and find out a little bit more. I mean, I'll just go back actually, because what this is implying then is that there is some sort of advection going on of warm and salty water, especially in the boundary current region, because the ocean has to be losing heat. Okay, we've got positive heat fluxes out of the ocean, so it has to be losing heat. But why is it getting warmer and more salty in the boundary current region? Well, it has to be because of an advection of warm and salty water, or warm and salty water is getting in there somehow. And we've demonstrated this by using some one-dimensional modeling. So this is using a mixed layer model of the ocean, the PWP model for those who know that sort of thing. And the observations here are in red and blue. So red is from the early period, blue is from the later period. And the shading is giving an indication of the range of the profiles that we've used. So you can see in the left panel, the temperature, we get a relatively warm profile, and it's cooling over time, going from here to the blue profile here. There's a change in salinity, as we saw previously, and then change in density in the observations. And the model simulation in black does a decent job of capturing this. So it captures the cooling. So the model simulation is the simulation at the end of the cold air outbreak period. Okay, so you'd expect it to lie over the top of the blue line if it was perfect. And for density, it pretty much does lie over the top of the blue line. So it does a very good job for density, this one-dimensional model. But you can see for temperature, the model does a bit too much cooling and not enough salinification. So this is also indicating that we're missing out on some advection of warm and salty water. And as I say, this is for the interior region. We've done similar approaches for the boundary current region, and the model's a lot worse because this advection factor is dominating there. But it is more complicated than that. We've also got data from the mooring, which I'm showing here as a time series, so this is fixed in location. And you can see I'm showing in this bottom panel, this is temperature, and the black line is mixed layer depth. And you can see, and the top panel is observations of total heat flux from the buoy. And what you can see is some cooling associated with the loss of heat, so this period of cooling here, for example, and another period of cooling here. And that leads to a deepening of the mixed layer, typically. And when that happens, you can sort of burrow down into this warmer layer of water here, which then mixes up some warmer water towards the surface. So this is a sort of one-dimensional warming effect as well. So there's a couple of things going on. So to move to my conclusions, comprehensive observations show a well-observed weak to moderate cold air outbreak. The ocean responds by cooling and deepening, particularly in the interior of the Iceland Sea, but this is masked a little bit in the boundary current regions where advection and eddies and this burrowing down into the warm layer dominate. So in some way, the ocean response to the cold air outbreak is dependent on the region. And I'll stop there. Thank you.
Thank you, Ian. So we have time for questions. Yes? Vito? Marie? Yeah.
Just a curiosity, because in your slides about the effects, seems then the impact in the interior is bigger than on the boundary. Any suggestion or explanation?
So I think the boundary current the boundary current is associated with stronger advection at depth. And I think that stronger advection at depth is leading to more advection into this mixed layer as well. So warmer and salty water being advected in there. But I think there's also other things going on. There's more bathymetry, more complex bathymetry in the interior region, which is probably contributing to some topographically forced eddies in the ocean, which is leading to some complicating factors. So there's a lot more variability in the ocean than one might imagine.
Okay, thank you. I think we should... yes, the last one.
Thank you. Ian, nice talk. Now, this may have been more aspects for your some of your oceanographic collaborators, but the Atlantic water layer you were showing, do you or any of them have any idea if it just recirculated interior of the Nordic seas or may have gone up into the Arctic Ocean and then be recirculating southward?
I don't think we can answer that question for that specific layer, but as part of the wider IGP project, we have some of my collaborators, Jay Hung at Woods Hole has looked into some of those questions and been using SPICE to, is that the word? To sort of do some trajectory analysis and answer those sorts of questions. So he's got a nice paper from 2021 in Nature Comms which addresses that. Oh,
thank you.
Yeah. Okay.
Thank you, Ian. During your talk, I changed my acronym merged observatory data file into a verb, and we would really like to MOD